Hello, this is the fourth video in the fifth complex number series on complex roots for OCR Pure Core Further Mathematics, and we will see how to solve equations using complex roots. You've already seen how to solve the following types of equations, or z to the n equals 1, and z to the n equals w, where w is any complex number, including ones where the solutions are wholly real. These are the same as finding nth roots of, or solve the equation z to the n minus w equals 0. In previous videos we saw that the solution to z cubed equals w lay on a circle and formed regular polygon, in this case an equilateral triangle. Now imagine translating that circle so the centre is some complex number a plus bi. You would then find that you had a situation where z minus a plus bi, and if it was a cubic equation then cubed, equal to w. In this example, an equilateral triangle on an Argand diagram has centre 2 plus 3i and one vertex 4 plus 3i. So if you can imagine, you're probably going to have the other two vertices about there and there to form the equilateral triangle. We need to write down the equation whose solutions are represented by the vertices of this triangle, and then later find the other two vertices. Because we know the centre, we can therefore write down z minus this 2 plus 3i cubed equals w, and we just need to identify w. Well, we know that we have one root, the 4 plus 3i. So let's substitute that in to find w. So we have 4 plus 3i minus 2 plus 3i cubed. You can see that the 3i's will cancel out, leaving us 4 minus 2, or just 2 cubed, equal to 8. So in this scenario, w is the real number 8. Sometimes you may be given the equation as the starting point of the question and asked to show that the roots form an equilateral triangle. So having found this equation, we now need to find the other vertices. Well, we know that one of the cube roots is 4 plus 3i. We just need to find the other two. Remember, we just need to take the cube roots of a modulus and the argument. First of all though, let's write this real number 8 as being 8 of cos of 0 plus 2k pi plus I sine 0 plus 2k pi, where we know that k can only take the values 0, 1 and 2 before those roots would start repeating themselves. We know that the r value for all the z will be 2, because this is the cube root of 8. And we know, because cube rooting, that we'll be dividing the argument by 3. Let's have a look and see what happens when k equals 0. We know that z minus 2 plus 3i will just equal 2. because cos of 0 is just 1 and the sine of 0 is 0. That would lead us to the first root, which we're expecting, of 4 plus 3i, which you remember we were given in the question. When k equals 1, we have that z minus 2 plus 3i is going to be equal to 2 lots of cos of 2 pi by 3 plus I sine 2 pi by 3, and we can work that out in our calculators. Similarly, for k equals 2, we know we're going to get cos, in this case time, 4 pi by 3 plus I sine 4 pi by 3. So using our calculators we can get these values here. And rearranging, in other words moving the minus 2 plus 3i to be added to the other side, leads us to the root we knew about and these two new vertices that we were asked to find. As you can see in the diagram, they do indeed form an equilateral triangle and all lie on the circle centre 2 plus 3i. This is the final video of the 5th complex number series on complex roots.